Hello to everyone at the European Lisp Symposium, and thanks for hosting me today. I'm Andrew Sengel, and I'll be demonstrating April, a compiler from APL to Common Lisp. First, an overview. APL, which stands for A Programming Language, is a computer language specialized for linear algebra and operations on arrays. In APL, you can do dramatic array transformations with just a few characters of code. APL originated a family of languages called the vector languages, known for their terse syntax and a focus on working with structured data. The languages J and K are both APL descendants. APL is notable for its use of a custom character set. It has characters unique to it that it uses to represent its functions and operators. Each of the core APL functions is represented by a single character, and other characters are used as operators, which can be combined with functions to produce yet other functions. Now for some historical background. While APL and Lisp may seem very different, they have some surprising parallels in their history. Both languages had their genesis in the late 1950s, and both were originally designed as mathematical notation. The APL notation was created by Kenneth Iverson, a Harvard mathematics professor, as a new way of writing linear algebra expressions. Like John McCarthy, he did not at first anticipate that APL could be evaluated using a computer. His colleagues built the first APL interpreter after making some simplifications to Iverson's original notation, just as John McCarthy's students moved from M expressions to S expressions to build the first Lisp interpreter. APL became prominent on mainframes, in particular the IBM System 360, and APL typically worked as a complete operating system on the machines where it ran the same way that Lisp did. On those systems you had, for example, functions to send messages to another user's terminal. Unlike Lisp, though, there was never a mainframe APL machine with hardware designed for APL from the ground up. The original APLs were used with teletype terminals that required a specialized IBM typeball, which you can see in this picture. Today, APL characters are usually entered using a special input mode for your operating system of choice, where you use a moderator key to type the APL symbols. Here you can see how APL symbols are laid out on a standard keyboard. Lisp and APL had the same problem when the microcomputer revolution happened. Garbage-collected languages were too slow to be used as much more than toys on a 1980s microcomputer, and with APL in particular, it's easy to write programs with massive memory and processor usage when doing certain array operations. Today, the phones we carry around in our pockets are thousands of times faster than a mainframe from back then, but the legacy from that time is still with us. It is notable that APL powered one of the very first microcomputers, the MCM70 from Microcomputer Machines, which you can see here. Microcomputer Machines ultimately failed, and since then the language has been obscure. Today, APL is used heavily in insurance companies and in some engineering applications, particularly within the automotive industry. And now enough about history, let's get started using April. April is included in QuickLisp, so you can get an older version by evaluating QL QuickLoad April. For the most up-to-date version, it's best to install from the GitHub repository. We can start by writing a basic Hello World program. And a basic array operation. To create a vector in April, you just need to enter a series of numbers separated by spaces. As we can see above, APL can compose scalar math operations, so when you write this 1 plus 1, 2, 3, the 1 gets added to each element in the vector. Now let's move on to some of APL's specialized functions. A function that you'll see a lot in APL is the iota. It simply gives you a vector of integers up to a given number. And next we'll look at the shape function. The shape function can reshape an array into a given set of dimensions. Here we're taking the iota 5 and repeating it in row major order to fill this 3x4 matrix. Something else that's helpful to know about is the April-F macro. By passing April-F, you can get the APL-style printed representation of an array as well as returning the actual Lisp value. APL's printing format you see here can be more readable than Lisp arrays, but these printed representations aren't usable as code the way that Lisp's representations are. Most of the functional characters in APL can be used to invoke both monadic and dyadic functions. A monadic function takes one argument and a dyadic function takes two. For example, take the row shape function above. It's being given two arguments here. On the right, the iota 5, and on the left, the vector 3, 4. telling us to make a 3 by 4 array out of iota 5. The iota 5, on the other hand, this iota is being called monadically with just one argument. So let's find out what the shape function does when called monadically. It simply gives us the shape of its argument. 3 by 4 matrix gives us the vector 3, 4. So we can quickly try a few more functions here. This is the rotate function. It's not a Greek letter phi. It's supposed to represent a sphere being rotated about an axis. When I give it this matrix, it flips the matrix on its last dimension, reversing it, horizontally in this case. Now let's try giving it a left argument, calling it dyadically. And in this case, it rotates the matrix 1 degree. And if I give it an argument of -1, it rotates the matrix in the other direction. Notice here the high minus character. This is used instead of the regular minus sign, since APL uses the regular minus sign as a function. If I were to give the regular minus sign here, it would negate the rotated matrix instead of rotating it the other way. Another important thing to note is axis arguments. In this case, I give the axis 1 argument to this function, and that causes the rotation to happen on the first axis, the vertical axis, instead of the horizontal. This function by default will rotate on the last axis, but it could be used on any rank of array on any axis by using the axis here. So you pass axes by putting in brackets a number and putting it right before this function. So let's now explore the comma function. The comma, monadically, is ravel. It simply unravels the array into a vector. And the dyadic form is called catenate. Catenate can glue together scalars and arrays, or arrays and arrays. In this case, we're gluing a column of 9s onto the left side of this matrix. Catenate can also be used with axis arguments. By passing axis 1, we're gluing 9s onto the top. Now let's try gluing an entire matrix on, and here we're gluing this 3 by 3 array of 9s onto the left side of the matrix. Lastly, we're going to demonstrate assignment. So here we assign this 3 by 3, 4 row out of 5 to the variable m. This left arrow is used for assignment. It's pronounced gets by APL users, so we say m gets 3, 4 row out of 5, and then we do m comma m. This diamond character here is simply a statement separator, used kind of like the semicolon in algal family languages. So we're gluing this matrix to itself. The next thing to explore is operators. An operator in APL is a type of function that can take functions or a combination of functions and values as its arguments, and then returns another function that can be then called on values. To see a simple example, let's check out the commute operator. So this function here, the tilde with an umlaut, is called the commute operator. And it does the same thing as the above. So when you combine a functional character with commute and then give it an argument, it treats it as though you gave the same argument to both sides of the function. And what this means is I no longer need to do this assignment in order for this to be expediently writable. And that's a basic example of APL golfing. Now, what happens if you give a left argument to a function composed with the commute operator? It reverses the order. So it's as if the 9 were the 9 and the 3, 4 row out of 5 were flipped around. So it glues 9s onto the left and bottom instead of the right and bottom instead of the left and top. One more operator is another essential APL operator. is the outer product. So taking this jot dot multiplication sign gives us the outer product of multiplication, and giving it two iota 10 vectors produces the classic 10 by 10 multiplication table. Another thing this illustrates is that in APL, evaluation goes from right to left. So the first thing here is I evaluate the iota 10, then I compose this function, this outer product via multiplication, and then in the parentheses, this is evaluated before it's given as the left argument. Without the parentheses, it would be the 10, and then the iota would take the result of all this. So that's something important to note. One more set of operators we'll go over is reduce and scan. Common Lisp's reduce function is expedient, but the APL function is even more compact. And the backslash is the reduce function. Notice one shortcoming of passing strings this way is that all backslashes need to be doubled. And that's the scan operator. So this has been a quick overview of APL and April's basic syntax. Now for some background on April. My first experience with APL was in 2016. I was working on learning K and had some trouble figuring out the syntax, so I tried my hand at APL, since I'd heard it was the original vector language. Arthur Whitney, the creator of K, was a student of Ken Iverson. And once I tried APL, it immediately clicked, and I understood the lure of golfing, accomplishing a task with the shortest possible program. Looking at Lisp, for all of Lisp's semantic strength and the ability to create a custom syntax for a given problem, dealing with arrays in Lisp can be cumbersome. The code can get verbose when you're writing lots of make arrays and loops and aref forms, meaning that APL's strong point is located squarely at one of Lisp's weakest points, and this gave me the inspiration to combine the two languages. I started on April in late 2017, and since then it's gone through lots of evolution. Just about everything in the compiler has been re-implemented 3 times or more. Since my original Lisp NYC presentation of April in September 2020, I estimate that the language's codebase is about 95% different. The picture here gives an engineering analogy to April's use within Lisp. In this EEPROM microchip, the actual integrated circuit is tiny compared to the size of the hardware needed to connect it to the rest of the system. The same design pattern can be seen in this code, which was used to create a palette shifting SVG animation. It's time to talk a bit about April's top-level design. An interesting feature of April is that the language is built around a core specification. This specification can be found in the file spec.lisp, which we're looking at right now. Most of spec.lisp is an invocation of one giant macro called specify_vex_idiom. The idiom being specified is called April, not surprisingly, and inside we have some default system values, this profiles section that groups unit tests into some different categories, and these are utility functions. For example, this one matches the characters that can be used inside a variable name, and this prep code string removes comments. Below that, we have the April system variables and functions, the quad symbols for those familiar with APL. And next, we have the real meat of the spec, the function and operator listings. Here is April's plus function, used to add things together as we just saw. And each function spec contains different pieces of metadata. For instance, note the function's identity value. The identity for addition is 0 because 0 plus a value equals that value. And for multiplication, the identity is 1 because 1 times a value returns the same value. So one place these are used in APL is when reducing an empty vector. So using the reduce operator that we saw, if I reduce the Zilda, this character stands for an empty vector. By addition, I get 0. Reducing it by multiplication gets me 1. So the spec also notes if functions are commutative, and it lists their inverse forms if they exist. So for instance, multiplication and addition are commutative. These are the inverse forms. And then going through the list of functions, we can see that each one has a set of unit tests. So the unit tests, for somebody reading this, actually kind of document what the function does. So going through the scalar functions, we arrive at the logical functions, less than, equal to, greater than, not equal, the and the or. And now we're into the array function. Here's the iota and row that we were looking at before. Continuing on, we get to rotate. And after the functions, we reach the operators. Here's the reduce and the scan. And then the inner and outer product operator we were looking at. And then after operators, we have many more of the unit tests. And these unit tests can be invoked by entering April test, and they also do double duty as a set of demos. So entering this prints a long list of demos, and these demos constitute a kind of top-level documentation, a kind of brief overview of the language. April is the only language implementation I know of that's based around this kind of centralized spec. A student or somebody wanting to learn about vector languages can start at this point to get a bird's eye view of the language and then investigate whatever implementation detail interests them. For instance, starting from here, we can find the count to and index of functions mentioned here. And we can find its implementation in the top-level language library, the functions.lisp file. Let's take a look at another fun April demo, the ncurses application. This demo includes the classic Conway's Game of Life APL function, which you see here, but rather than displaying the life matrix directly, it uses this stencil operator to implement a convolution kernel that draws outlines around the cells using these box drawing characters. Let's start it up in the terminal to see how it works. This program gives you a simple interface. Pressing G draws the next generation. Here we see one generation after another. Pressing R will reset the simulation with a random matrix, and you press Q at the end to quit. Now observe that the outlines are drawn around each of the cells in the life matrix. Then these background colors for the characters are used to indicate the presence of cells over time. So cells aren't ever actually drawn, you just see the presence of cells at a given time. So this color, the lightest color, indicates that there's been a cell in that location for each of the last 5 generations. And this shading outside of the lines, which you see here, this reflects the ghosts of dead cells. There's no outline, so there's no cells at these positions in the present, but there were in the past. With all that said, you may have some questions. In particular, you may want to know, what are those color-changing lights back there? Let's find out. Behind me is a device called Bloxel. Bloxel is the product of a hardware startup, and we call it a luminous structural display. Bloxel is fundamentally a building material, transparent acrylic blocks that you can use to build walls and windows, and each Bloxel block contains addressable RGB LEDs at its 4 corners. The blocks are individually controllable and behave as pixels, linked together and driven using a controller board connected to a larger computer. Since each block is 6 inches square, the Bloxel is a quite low-resolution display, and this limitation fuels creativity in the design of Bloxel patterns. Bloxel is unique in that it is at the same time a building element, a light source, and a visual display. I know of nothing else that fills all 3 of these roles. You're currently watching video from a live stream done using Bloxel during the pandemic when there were no options to showcase it at live events. At different times, Bloxel animations were set to run automatically, to synchronize with music, and to be controlled via a live VJ system. Bloxel is April's flagship use case. The combination of APL and Lisp has allowed for unprecedented flexibility in the design of software and animations for Bloxel. With Lisp, I defined semantic structures for building animations, controlling playlists, and specifying interactions between the blocks I'll display in other devices. With APL, I can create pixel graphics and color palettes almost as fast as I can imagine them. The code you're looking at is a Bloxel animation spec. The APL lines specify effects that are particular to this animation. APL's brevity allows me to specify these custom effects directly inside the spec without increasing its length by much. If I were using Common Lisp, my choices would be to either write many lines of custom animation code directly in the spec and drastically increase its length, or collect the custom animation functions in another place, adding the cognitive and maintenance overhead of many collected functions that are each only used for a single animation. And by the way, the color patterns that you saw on the Bloxel behind me were all created with this line of code. It produces random RGB color sequences of varying lengths. I realized I could do this when I wrote a function to simply turn off the Bloxel by sending a series of all zeros to it, and I found how easy it was to tweak the color sequence. It took me only a few minutes to write this algorithm and then use it to generate a library of pleasing color combinations. I doubt such fast iteration would be possible in a more verbose language. And with that, it's time to open the floor for questions.